What's up, guys? I have a name, and today we're gonna make something to throw water bottles into the sky really high, but higher than that, and cut. Okay, so the first thing that we need is some PVC to make our rocket launcher. And the second thing is more PVC because third thing, glue. And then fourth, the most important part, all the random junk in this bucket. And then all you do is wrap all that up in your tarp. Then once you have it all wrapped up, you're gonna need some heat. Here, guys. Now that you have that done, you're gonna let all of your stuff sit for just a minute. So go ahead, clean up your area, and just, chill out for a little bit while you just sit here, wait, maybe learn how to and then just like that, you're done. Go ahead and open your TV up. And there, you'll find, voila! Come on. A beautiful rocket launcher. If you're gonna want to be building one of these on your own, there's a couple things you need to know. The actual design of it isn't that important, but you're going to want 1/4 inch PVC, that's so that your bottle fits over the end. If you look there, it's a thick kind, so it's pressure rated because we're going to be pressurizing this. And then you're going to want a bike pump of some sort, or one of the nozzles for it. So you can get these for like $4, usually in the lawnmower section because they go on like the bigger rubber wheels of the lawnmower at Home Depot or Lowe's. You're going to want to put that screwed in and then glued so that it's sealed tight into a piece. I prefer these little caps that go on the end of the PVC, and then here at the end, this is our launching device, which we'll get into more later. And now it's time to shoot off some rockets.
Your regularly scheduled program has been interrupted for science. All rockets work off the principle of Newton's third law of motion, that being, every action has an equal and opposite reaction. So, the force required to send the fire and gases out the back is the same as the force pushing the rocket up into the air. Another way to look at our rocket is by momentum. Momentum is some social construct that equals the mass times the velocity. Notice it is velocity, not speed. Velocity is just speed with direction, aka it can be negative. This will help us later. It's the classic physics problem. An astronaut that weighs a certain amount throws a wrench that weighs a certain amount. If the astronaut is now moving backwards at this speed, how fast is the wrench moving? We can solve this based on the principle that momentum is constant in an isolated system, or a system with no external forces. Our system is then the wrench and the astronaut. If we assume they are both at a standstill when we start, velocity is 0, and therefore momentum is 0. We assume no air friction or gravity is a factor because we are in space, so therefore, this equation must always hold true, because there's no external forces. We can then split the momentum of the system up into the sum of the momentum of the astronaut and the momentum of the wrench. When he throws the wrench, the velocity of the wrench will be the negative of his momentum divided by the mass of the wrench. This is a one-dimensional problem, which means that everything is moving on the same line. However, this principle holds true in all 3 dimensions. Your velocity vector just gets more complicated. But wait, you might say, we aren't throwing a wrench. You're right, so let's simplify down our water rocket to a cylinder and a disc of water. As I'm sure you can see, as we shoot the disc of heavy water downwards, our bottle will be going upwards at much greater speed, since it's much lighter. Also, we aren't in space, so we do have outside forces acting on our object, so this equation will not always be 0. If it was, then our bottle would never come down, which doesn't make much sense. We have two main forces, gravity and air resistance. The force of gravity near the surface of the Earth is just the mass of the object times 9.8 meters per second squared. Air friction is negative 1/2 the density of air times the cross-sectional area of the object times the drag coefficient. All of that together is just a negative constant for our purposes, and then all of that times the square of the velocity. So, why does all of this matter? According to Newton, force equals mass times acceleration, or acceleration equals force divided by mass. Let's say a rocket takes 1/10 of a second to expel the disk of water and accelerate to, let's say, 35 meters per second, about as fast as you can likely throw a baseball. In that time, the deceleration due to gravity is 0.98 meters per second, not that significant in comparison to 35, and the deceleration due to air friction will be nearly the same. So basically, the difference in speed in the short time is less than 2 meters per second, between if we were in space or if we were on the Earth's surface. Because of this, we can use this model as an approximation of how fast the bottle will be going right after it is launched. Now that we have those principles in our pocket, we can move to the actual design of our rocket. We have a bottle that we cap. It's filled partway with water and partway with air. We pump more air in to pressurize it. Then, we release the cap, the water shoots out the bottom, and our rocket flies away. We can break our design down into 3 parts: the rocket, the capping and release mechanism, and the correct air-to-water ratio to get the max height out of our rocket. For our capping and release mechanism, I started with our 1/4-inch PVC pipe. The end of the bottle slides over the pipe, so I then melted the pipe and squished it together to make a slight bulge. This stops the bottle from sliding down any further and also provides a seal to keep the water in the bottle. I then used zip ties to hook around the lip of the bottle and a larger diameter tube to go around the outside to keep the hooks from coming off until we are ready to launch. I used a piece of an old broken vacuum cleaner, but anything that will hold the zip ties in place and you can release quickly will work. The second part is the rocket itself. We are going to be assuming that it will be flying empty for most of its flight. If the idea is to get as high as possible, let's make a parameter for us to maximize. Let's call it our adjusted initial velocity. It will be our true initial velocity minus the velocity we will lose due to air friction on the ascent. Since acceleration due to gravity is constant, we know that the height that the rocket will go will be proportional to this adjusted initial velocity. So now, to maximize this equation, let's first minimize our air friction. Let's start by minimizing A. The cross-sectional area of the bottle is obviously smaller when it's facing straight up rather than sideways. So, to keep it facing this direction, let's add fins to make it aerodynamically stable.
Next, C is a shape factor, so nose cone will reduce this coefficient.
Now, you might see that there is a balancing act here. The smaller we make the mass of the rocket, the higher the initial velocity, but also the larger the term on the right, because the mass on the bottom is smaller and the velocity is larger. But as we make the mass larger, the initial velocity is smaller, but so is the term on the right, because the mass is larger and the velocity is smaller. Remember this when designing your rocket. Now we get into the same balancing act with the water level. The more water we push out, the faster the rocket gets launched. However, the speed at which that water gets shot out is just as important. So we need to make sure that we have enough air to fully launch all the water out. But instead of doing math on this one, let's just go outside and test it.
So now we have our rocket built. It's pretty simple. I didn't go much into the actual building of it because that's up to you. You can decide what you want to do. You're just going to need the basics, your fins, and some sort of nose cone. Your nose cone is more than just for aerodynamics. This doesn't have any parachute, so whenever it comes down, it's going to be landing nose first on the ground. So give it something with a little bit of squish. I've seen people like tape tennis balls on the top. That'll work. I did not use a standard 2-liter water bottle. I used a 1-liter life water bottle, so it's really long, and that'll help us because if you can see right here, we have tick marks along our bottle, and what we're going to do is fill it up to different water levels and see which one goes the highest. Here's that launching mechanism we were talking about earlier. We have our twist ties here, and they hook around the lip of the bottle. Then we have this bigger pipe that slides up over the top to hook them on, and then whenever we're ready, all we do is drop this pipe and it goes shooting off into the sky.
When we were recording this, it was so windy outside that you really couldn't hear what I was saying, so you just get a voiceover instead. At this point, launching your rocket is pretty self-explanatory. Just pressurize it to safe pressure. 40 psi is well under the breaking point of most soda bottles. Our method for finding which water bottle went the highest was pretty simple. All we used is a stopwatch and my eyes. I would start the stopwatch right when I launched the bottle, then I would stop it as soon as it hit the ground. We did this multiple times at each water level so that we could get an average and our data would be more accurate. Which means we shot this bottle a lot.
3, 2,
Like,
1.
a lot.
One. All the way up. 1. 1. So now we're done. We have a really beat up water bottle and we're a little wet. So what did we learn? First thing, wardrobe continuity throughout a video is no fun, so I'm wearing something else right now. Second, if we look at our graph, you can see that we had our best performance somewhere between my second and my third tick mark. I went and I measured this out later. That was about 380 milliliters of water. So now that you have all this new information, go out and try this on your own. Go ahead, build yourself a water bottle rocket. If you don't have the ability or the resources to build yourself a launcher like this, go ahead and just get a wine cork with a needle for pumping up balls put through it, and then attach that to a bike pump, and there you go. You can launch it off yourself. Go ahead, experiment. Try different levels of water. Try different weights or different numbers of fins. Record your data, and hey, send it to me in the comments section. I'd love to see what you come up with on your own. Go ahead, have some fun, do some science, and remember, don't talk to any of your friends because we all have the coronavirus.